Hey everyone, so today we're going to be looking at polyatomic ions. Polyatomic ions are a group of covalently bonded atoms with a charge. With your AP chemistry classes and in my AP chemistry class, remember, we always have to memorize a fat list of polyatomic ions. And here's a few ways that will help us memorize some of these polyatomic ions. This will also go over how to use polyatomic ions in the world of nomenclature. So let's get into it. So remember, a polyatomic ion is going to be a group of covalently bonded atoms with a charge. Some examples of these are going to be the negatively charged polyatomic ions, sulfate, nitrate, and acetate. Now, at the end of the day, these, in my opinion, are probably three of the most important polyatomic ions, and you should really know these. You should just know them very well. Sulfate is SO4, so there's one sulfur and four oxygens with a -2 charge, so there's 2 extra electrons that this entire particle has. Nitrate is NO3, 1 minus. It has 1 nitrogen and 3 oxygens with 1 extra electron. And the acetate polyatomic ion is C2H3O2 with a 1 minus charge. Yes, you should know all of the polyatomic ions. Now, with that being said, okay, a polyatomic ion, while they are and do have a group of covalently bonded substances, so they are covalently bonded, they are always a part of an ionic compound. What I mean by this is that if the polyatomic ion is negative, it's probably going to be bonded to a positively charged cation, and vice versa. If your polyatomic ion is positive, it's going to be bonded to some sort of negatively charged anion. So for example, if we're looking at sodium chlorate, sodium is the positively charged metal ion, Na1+, something we're probably fairly familiar with due to the fact that it's in the first column on the periodic table. Chlorate is another good polyatomic ion to know, to have memorized. It is ClO3, 1 minus, 1 chlorine and 3 oxygens, and that whole subunit, that whole particle has a charge of -1. So if the charges are +1 and -1, these two ions will come together in a 1-to-1 ratio. The formula for sodium chlorate is NaClO3. So once again, while polyatomic ions are usually multiple nonmetals combined, they themselves are not molecules. What I mean by this is that they will always be attracted to some other oppositely charged subunit. A really great example of this, let me go ahead and write this down, is sulfite and sulfur trioxide. So when I'm referring to sulfite, I'm referring to the polyatomic ion SO3 with a 2 minus charge. This polyatomic ion will probably be bonded to a magnesium, which has a 2+ charge. It could be bonded to sodiums, which have +1 charge, etc., etc., etc. Sulfur trioxide is a molecule. And it's SO3. It has 1 sulfur and 3 oxygens, no charge. This is a gaseous molecule at room temperature, and it acts and behaves as molecules do act and behave. So once again, this group of polyatomic ions is often bonded to metals. Now, as far as naming polyatomic ions, compounds with polyatomic ions, you pretty much want to follow the same rules that we established for naming binary ionic compounds. So if you have a metal, right, and that metal is a transition metal, you want to use Roman numerals for that metal. All of that still applies. The only thing that changes is that your polyatomic ion could be a cation, or it could be an anion. Most of the time they are anions. I will say that most of the time, not all the time, but for AP chemistry, most of the time they are the anion, meaning you will name the metal as is, and then you name the polyatomic ion as is. So let's go ahead and try a couple of these out. The first one we are looking at here is KNO3. Well, we know that the metal is going to be named first, K, and that is potassium. potassium. Luckily, potassium is not a transition metal, so I do not need to indicate or figure out the charge of that. NO3 is the polyatomic ion nitrate. So this is going to be potassium nitrate, potassium nitrate. And as far as this molecule goes, it has a positively charged K and a negatively charged NO3, and the attractive force between the opposite charges is what brings them together. The next one we have here is CuClO2, CuClO2. So we know that the first substance is copper. Now copper is a transition metal. Copper is a transition metal, so I will need to indicate the charge of it using a Roman numeral. And I figure out the charge of copper based on what it's bonded to. It looks like ClO2 is the polyatomic ion chlorite. It is the polyatomic ion chlorite. In chlorite, it has a charge of -1. So in order for copper to come into contact with it in a 1-to-1 ratio, copper must have a charge of +1. So this is going to be copper 1 chlorite. The last one that I have here is going to be CaCO3. Ca is the metal calcium. Calcium is not a transition metal, so I don't need to use Roman numerals for it. CO3 is the polyatomic ion carbonate. So this is going to be calcium carbonate. So with that being said, I want to remind everyone that when we write formulas with polyatomic ions, the miniature subunits indicate the amount of the polyatomic ions present in that ratio. If there is more than one, you want to place parentheses around the polyatomic ion and use a subscript to indicate the amount. So for example, if we're looking at barium nitrate, which is the formula BaNO3 2, BaNO3 2, notice I don't have to say parentheses when I do that. There are 2 nitrate polyatomic ions. Essentially, for every one barium, which has a 2+ charge, we'll have 2 nitrates, which have a -1 charge, which have a -1 charge. And the attractive force between pluses and minuses is what brings them together. Now, of course, this is a crystal lattice, so you're going to have positives and negatives going in a lot of directions, up, down, left, right, in and out of the plane of the crystal. But once again, in that crystal, for every one barium, you have 2 nitrates. So when we're writing formulas, it follows the same rules. We want to make sure that the formula represents a neutral formula, and this is all based on the charge of the thing that is participating, the charge of the ion that is participating in the compound. So aluminum being in the third column is going to be Al3+, has a 3+ charge. Acetate, being one of the polyatomic ions you have memorized, is C2H3O2 1-. That means that when this forms a compound, we need 1 aluminum for every 3 acetates, and acetate is C2H3O2, and there are going to be 3 of these, so we represent this with the parentheses 3. Magnesium phosphate, well, we know magnesium has a 2+ charge. Phosphate is going to be the polyatomic ion PO4 3-. And if you use the cross-down rule, we know that we're going to have 3 magnesiums, and 2 phosphates, and we represent the 2 phosphates. We write phosphate down once and parentheses and a 2 on the outside. And then the last one is tin for sulfate. We love Roman numerals because Roman numerals tell us the charge of the tin molecule. In this case, it's 4+. Sulfate is SO4 2-. Now, the cross-down trick won't necessarily work for this because remember, we want to represent ions in the lowest whole number ratio. And in order to do that, we're going to go ahead and bring together 1 tin for every 2 sulfates. 1 tin for every 2 sulfate. And that's because sulfate has a -2 charge, and 2 times -2 is -4, which ends up canceling out with the +4, Awesome. So there's an extensive list that I have online of polyatomic ions that you should begin to memorize. And if you have any questions with that, you can shoot me an email and I'll help you out with that. Good luck. Have a great day. See you guys soon.